Good afternoon, everyone. I just wanted to say, first of all, thanks very much indeed for everybody at Construction News for putting on this fantastic event these last couple of days. And also a big thanks to all of the guys behind the scenes, all the tech guys that are hopefully going to make this go really, really smoothly over the next 20, 30 minutes. Yeah, better get started. As it says there, my name is Chris Newman, and I work as a zero carbon design manager for Mitsubishi Electric. My job is kind of to help my colleagues, our clients, to try and understand this rapidly changing world of sustainability, legislation, technical guidance, and then try and sort of demonstrate how our products can fit into that and how they can help deliver the outcomes that everyone is trying to achieve. As it says, the title of the presentation is Retrofitting for Net Zero, and we're going to look at heat pumps for decarbonisation. So I thought I'd break this session down into three kind of short sections, really. Talk about why we're talking about retrofit, what exactly is the commitment that we've got, what are the market size, what are the drivers in the market that are pushing everybody towards retrofit, and a little bit about heat pumps. Why are heat pumps being seen as the method to decarbonise buildings? What is their operational carbon impact? What's their embodied carbon impact and their whole life carbon emissions, to try and make sure that they're the right solution. And then very briefly at the end, we'll just look at a couple of example products and the type of things that they might be able to achieve in this arena. And obviously we'll finish with some Q&A. So why are we trying to get to net zero? Well, back in 2019, Chris Skidmore signed a document that legally committed the UK to achieving net zero carbon emissions by 2050. Now, this was an increase from the original 80% reduction from 1990 carbon emission levels, which was part of the Climate Change Act in 2008. And obviously, this increase put us on a pathway towards net zero by 2050. So the way that we kind of look at this now is that effectively all roads lead to net zero. But it's a little bit like having a destination with no map. There's lots of different ways to get there. Everybody is on a different pathway. Some people's pathway and some people's journey is going to be a lot easier or a lot more difficult than others. And some people are an awful lot further down the journey than others are as well. But ultimately, we are all heading to the same destination. So as far as the UK government is concerned, the way that they looked at trying to get to net zero was by setting carbon budgets. Now, this was all done as part of the 2015 Paris Climate Agreement. And effectively, the UK's carbon emissions, or their nationally determined contributions to the overall global carbon emissions, are set over these carbon budgets. You can see carbon budget 1 and 2 have already finished. We're in carbon budget 3 at the moment, about to go to carbon budget 4. Now, over those carbon budgets, we just about managed to stay where we needed to be within the required amount of carbon emissions. And you can see there, though, that carbon budget 4 is actually quite a significant reduction in overall carbon emissions from where we currently are in carbon budget 3. And the lines that you can see that are overlaid over the top there, they're kind of different plotted trajectories that we could follow, depending on exactly how aggressively we go towards doing things like retrofit, and exactly how aggressive the policies are and the drivers are to make the UK decarbonise. Now, the grey line at the top, there's one that says steady progression line. That's kind of a line that we're on at the moment, really. It might just about get us to where we need to get to, but we're probably going to fall slightly short on carbon budget 4. But you can see by the time we get to carbon budget 6, we're going to be an absolute mile away from where we need to be. So we've really got to start ramping up our efforts to try and decarbonise. And as we try and do that, there's going to be an awful lot of policy levers that are going to need to be pulled, and an awful lot of incentives that are going to need to be generated to try and get everybody to take this path. So back in 2021, it was the Climate Change Committee, who are obviously a cross-parliament body that look at government policy, look at how the government are approaching their own targets and strategies. And in their review, they broke all of the different areas of trying to get towards net zero into these 5 categories of surface transport, buildings, manufacturing, construction, and so on. And you can see there the different colours relate to how well we are doing in those particular areas, and whether there are policies and strategies and plans that will actually get us on the right trajectory towards net zero. Now, obviously, in some areas, there are some green, which is good, which means that we know the data. We've got a good legislation or a good plan in place to try and get to that area. But you'll notice in the middle of the slide that the building section is a little bit sparse. There's quite a lot of areas where there isn't enough data, or there isn't enough policy, there isn't enough legislation, or it's simply too early to say. We don't know whether the policy is going to do what it needs to do, or we don't know whether the data is actually looking good or not. So I think there's definitely going to be an awful lot of change, as I said at the opening of this presentation, in the area of buildings. And when we look at buildings, we look across the UK, and this data comes from the government's need report. It tells us that there's about 1.75 million non-domestic buildings across the UK. Well, actually, to be fair, this report covers England and Wales. If you include Scotland and Northern Ireland, it pushes it up to about 2.2 million non-domestic buildings overall. But there's an awful lot of non-domestic buildings. Most of them, as you can see there, the vast majority are quite small, likely to be small retail shops. But the thing I found quite interesting is that around 6% of all non-domestic buildings across the UK are larger than 1,000 square metres. So these are pretty big buildings. But that 6% are using over 50% of the energy of all non-domestic buildings. So there's an awful lot of work that needs to be done, especially on larger buildings, to get their energy consumption down. And obviously, as a result of getting their energy consumption down, hopefully that will also reduce their carbon emissions as well. And when you look at the spread of the different types of buildings that we've got, everything from shops, hospitality, over 350,000 offices. They're more than likely going to be some of the larger buildings, along with probably a lot of the healthcare buildings, about 26,000 of those. But all of these buildings, no matter whether they are big or small, whether they are shops or hospitals, they have all got to decarbonise. They've all got to get to the legally binding committed target of net zero by 2050. And as I said, there's an awful lot of work to do. But when we look at these buildings today, we've got to try and assess, well, what does a good building look like? And the way that the UK currently decides what a good building looks like is by using energy performance certificates, or EPCs. And you can see on this slide here that the lower your energy consumption per square metre, the higher up your EPC banding you go. Now, in an ideal world, we'd have all of our buildings really, really high up that scale. But unfortunately, that's not quite the case at the moment. And in fact, to try and push those buildings along up that scale, the government introduced the minimum energy efficiency standards regulations, and they were starting to increase the minimum allowable EPC rating that a building could have. And you can see there in April 2020, they legislated to say that any buildings that were F or G rated, those buildings wouldn't be allowed to be let or leased, or new tenancy agreements signed. And obviously those buildings then start to become much less attractive, much less valuable, and hopefully that will be a big incentive for those building owners to increase the energy efficiency of those buildings and obviously reduce the carbon emissions associated with them. But that's not really going to get us where we need to be. So there was a consultation that came out of UK government back in 2020, concluded in 2021, about pushing up ratcheting up another minimum standard. And the outcome of that consultation is that it looks as if the government are going to legislate to say that non-domestic buildings need to get to EPC B by 2030. Now, around 85% of all non-domestic buildings are currently worse than EPC B. You can see in that chart on the right-hand side there. So that's an awful lot of buildings that are going to have to move an awful lot further up that EPC scale in order to try and get themselves where they need to be. Because if they don't move themselves where they need to be, there are some big risks. But you can see there on the slide that if we did get them there, we could be talking about over 10 terawatt hours of energy savings by 2030, and crucially, over 4 megatons of carbon dioxide savings by the time we get to that really steep budget, carbon budget reduction of carbon budget 5 in 2028. So effectively, what might happen If you don't drag your building up the EPC scale, you could end up with what's called a stranded asset. And you look there in 2030, all of those buildings that are C's, D's, or E's could quite easily end up fall into the same problem as buildings that are currently F or G's. Now, to be fair, the government are doing some really good work in trying to do some decarbonisation overall. One area that they've done that pretty well on is with the UK electricity grid. And you can see in the chart on the left-hand side, that's demonstrating the raw energy that goes into UK power stations and then the electricity that they generate coming out on the right-hand side for all of the various different sources. That comes from the Digest of UK Energy Statistics report. They typically come out every couple of years by the time the government have had a chance to reconcile all of the data. You can see on the chart on the right-hand side that that electricity that we're producing is increasingly coming from renewable sources, low carbon sources. If you look right to the far left-hand side of that chart, you can see that the vast majority of energy used to be generated by coal. And as we've moved towards the latest data set in 2021, there's a really big chunk of that which is now being produced by wind and solar and other renewables. And in fact, the latest data I saw was that over 43% of the total electricity generated came from renewable sources. So there's some real big gains in that area. When you actually look at the amount of carbon dioxide emissions that are associated with electricity, this chart shows you quite clearly that back in 1970, if you used a kilowatt hour of electricity, it would generate over 1,000 grams of carbon emitted into the atmosphere. Whereas if you use that same kilowatt hour of electricity in around about 2010, that was down to 500 grams of CO2 released into the atmosphere. Now, this particular data set was taken back in 2018. You can see that there was all sorts of different predictions as to what might happen with the carbon content or the grid emission factor, as we call it, of electricity moving forward. But interestingly, they were all pretty much going down, which is good. And in the latest data set that we can see that came out from the Future Energy Scenarios document, which I'll show you in a minute, that has got even more accurate predictions as we move forward. But you can see that building regulations here as part L needed to keep up to date with these changes in the electricity grid emission factor. And in the update in part L in 2021, grid supplied electricity was then reduced as its carbon impact down to 136 grams or 0.136 kilograms of CO2 for every kilowatt hour. So at least the measurement for building regulations is now actually keeping up with the decarbonisation of the electricity grid. And if you look here, these are the predictions from the Future Energy Scenarios document in 2022 as to exactly what we think the grid emission factor, the carbon content of electricity is going to do as we move forward, depending on just how aggressive the policies that we mentioned earlier start to kick in. But that 136 gram is a pretty reasonable figure that should probably get us maybe up as far as 2030. Certainly been looking at renewing it by then or reassessing it by then. But if we use that figure that's now in current building regulations of 136 grams of CO2 per kilowatt hour of electricity, and we actually plot that onto an example building effectively, you can see here that gas has got a grid emission factor of 210 grams. So for every kilowatt hour of gas that you consume in a building, it emits about 210 grams of carbon dioxide to the atmosphere. And if we take the part L typical default efficiency figure for a gas boiler in the UK, which is assumed to be 93% efficient, what that means is that to produce a kilowatt of heat, you've emitted about 225 grams of carbon dioxide into the atmosphere. Now, if we do exactly the same example, but with a heat pump, using the part L grid emission factor of 136 grams of CO2, using the part L default efficiency for a heat pump of 250%, which is not unreasonable, but you can better that if you want to. And that actually equates to only a carbon emission of 54 grams of carbon dioxide for every kilowatt hour of heat delivered. So it's a really big reduction there, around 76% of carbon emission reduction by simply switching your heat source from a gas-fired boiler to an electrically driven heat pump. So I think from an operational carbon emission point of view, it's fairly straightforward to see the trajectory, to see what's happened and what's happening, and then also to demonstrate how a heat pump, for example, would have a lower operational carbon emission than a boiler. But you guys in the world of construction, you know just as well as I do that it's not just about the operational emissions, it's about the embodied emissions. And we can see on this chart here that as we slowly but surely start to reduce the operational emissions, then the embodied carbon, which is the carbon that's gone in to physically make the buildings or make the products in this case, that starts to become more and more of a factor. And I think the current drive that everybody is aware of is to try and get more data out into the market about the embodied carbon of products and buildings so that we can start to make some better decisions overall. So from our point of view as Mitsubishi Electric, if you guys scan the QR code you can see on your screen there, that'll take you to our embodied carbon in the built environment brochure, where we're publishing all of our embodied carbon figures for our units, so you guys can start to have a look at what that looks like for your building. But I've done a couple of quick examples for you. So we took a 400 kilowatt gas boiler, pretty typical for a commercial building. We matched it up against 400 kilowatts of air source heat pump. This particular example is done against 580 kilowatt modules. And you see there that the gas boiler's embodied carbon is about 3,500 kilograms. And if I move on a slide, you can see that the air source heat pump's embodied carbon is over 69,000 kilograms. So there's a real big deficit on day one to make up. But based on that difference that I explained before about operational emissions, we know that over the whole life cycle of the product, the whole life carbon of those two solutions looks very different. You could be talking somewhere in the region of 5 times more whole life carbon emissions for delivering the same amount of heat from that gas boiler rather than from the heat pump. So I think that if you consider operational emissions and embodied carbon emissions and whole life carbon emissions, heat pumps still do seem to come out on top as being the right solution for decarbonising our buildings. So finally for today, I was just going to give you guys a very brief example of some of the products that we look at and what they tend to be able to help you with from a decarbonisation point of view. We kind of break this down into 3 key ranges: our Klimaveneta large capacity built to order products, our E-Series modular equipment, and our EcoDan equipment. And if we look at an example, we can see here that this MEHP unit, this is pretty much our most efficient heat pump that we make. Modularization is becoming more and more important. We're finding it really useful when we're trying to decarbonize buildings to take a modular approach. Usually because of plant space reasons, but also because it can often be a staged approach to where part of the building is done and then another part of the building is done. But this particular unit will get up to 60-degree water temperatures, a little bit higher as well. It'll do 65 down to -2 ambient. But this uses a reasonably low global warming potential refrigerant, fully inverter driven, and you can obviously get some reasonably big capacities from this machine. So we're starting to use this quite a lot from a decarbonisation project point of view. But to be fair, this is the unit that we probably see used most on decarbonisation projects. And the main reason for it is its incredibly small footprint. These units can bolt up against each other to give you around about 700 to 800 kilowatts of heat. And as I said before, because they're really small, we find it quite easy to fit them on existing buildings because, again, I'm sure you guys are all well aware, there is never enough plant space on existing buildings. But one of the downsides maybe to this unit is it will only generate up to about 55-degree water temperatures. And if that's not quite enough, then maybe you might need to look at another air source heat pump solution, which can generate up to 70-degree seawater. Slightly bigger, but it does use lower GWP refrigerant, full inverter driven, as I said, and these units cascade into groups up to 16 as well to give you over 600 kilowatts of capacity. So they're pretty appropriate for general decarbonisation projects as well. And then last of all is for hot water. Hot water is often a very easy target for decarbonisation, and we produce a CO2 QAHV unit, which is specifically designed for producing hot water all the way up to 90 degrees C to displace direct gas-fired systems, for example. So this is something that's starting to become quite popular. And across all of our ranges, really, you can see there anywhere from sort of 5 kilowatts for an individual home, right the way up to over 1,000 kilowatts for a large commercial building, and anything from maybe 50 degrees all the way up to 90 degrees. We think that there's there should realistically be an option for decarbonisation of heat on pretty much all buildings. So that's probably enough of presentation for me at this point. I think we're probably better off seeing if any of you guys were listening, if any of you guys had any questions.
Thanks, Chris. That was fascinating. Really interesting. First question I've got is just wonder if you can kind of give us a little bit of an overview of the state of the market at the moment in terms of client awareness of this. Is this knowledge and is the drive for these products widespread? And can contractors do something to reach the parts of the client market that you haven't quite reached yet?
Yeah, really interesting. I mean, I think there is client awareness is really quite widely known about all of this now, and there are a lot of clients talking to their supply chains to try and come up with solutions, especially clients that have set their own individual net zero targets. For example, although the UK is trying to get to net zero by 2050, there's so many organisations that are trying to get there a lot sooner, and their buildings are obviously a key part of that journey. So yeah, there's an awful lot of interest. There are some big challenges though about it. I mentioned a couple in the presentation, plant space being the obvious one, but also in trying to knit all of these things together. I think a big problem at the moment, I talked before about what good looks like, and good does look different to different clients. Some clients are very keen to get their operational carbon emissions reduced as much as possible, trying to get rid of their scope 1 emissions, for example, by getting rid of burning natural gas on site. Whereas other clients have got really strict embodied carbon targets. They're trying to retrofit buildings rather than knocking them down and rebuilding. And I think at the moment, that was where I was trying to go with that slide before. We're all trying to go to the same destination, but it's very, very different for different people at the moment. And I think given maybe another couple of years, maybe there'll be a bit more of coalescing to the same sort of route, but it is quite diverse at the moment. We're certainly not struggling to try and get enough people to want to talk to us, put it that way.
Great, that's good news. I've got a couple of questions from the audience here. First one is from David Knowles. How do we get over lower efficiency in colder weather when heat is needed the most?
So the way that we look at efficiency for heat pumps, we always look at a seasonal efficiency because you don't just heat on a day when it's, let's say, -5 outside temperature. You're heating across a heating season. So the important thing, yes, we do need to consider the efficiency on that particular worst case day, but we also need to bear in mind that I think off the top of my head, only about 2% of the heating season is spent below -2. So therefore, the vast majority of the time that the systems are actually delivering heating, you're actually warmer than those worst case temperatures. They tend to be for a relatively small part of the year. So seasonal efficiency is really important. And I think anybody who's trying to assess the performance of a heat pump system, there is a standard, BS-EN 14825, which forces all heat pump manufacturers to produce seasonal efficiency calculations for their units at different water flow temperatures, taking into account all of those different ambient temperatures, so that you get a reasonably fair appraisal of performance of different products.
And for that small number of days where we are in that zone where it's below the 2 degrees, are there obviously the technology is developing all the time. What at the moment is the kind of options there?
Well, I mentioned it briefly with a couple of the products I talked about, but most heat pumps that we offer to the market are physically able to operate down to about -20 external ambient temperature. Obviously, some perform better than others. Some are not able to do their full water temperature down to -20, but some are more than capable. I think I mentioned our CAHV unit as an example. That can deliver 70-degree water on a day when it's -20 outside. So I think from a client's point of view, yes, they absolutely need to be asking those sorts of questions and making sure that the products that they're proposing to use will do what they need it to do on those days when it is very cold. And we're all aware of climate change, so that probably means more extreme winters just as much as more extreme summers. But yeah, it is really important to look at a seasonal approach.
Yeah.
And as I say, it might not be the case that you go fully to heat pump. There's an awful lot of solutions about using bivalent systems where you use a bit of your existing gas-fired plant, for example, and you supplement it with heat pumps to try and get the best out of both technologies. Again, like I said, there's so many different ways to look at it. Everybody is trying to get there, but yeah, probably just engage with your designers and your supply chain to try and see what's best for you.
Interesting. Great. We've got a technical question here from Poppy Parsons, who's asking whether the heat pump embodied carbon figure you stated in the presentation includes the initial refrigerant as well as the constituent materials. And is that what's driving the difference to the gas boiler?
Well, thanks for that question, Poppy. I've been the lucky man, or part of a team of lucky people at Mitsubishi that have been doing an awful lot of work into the embodied carbon calculations of our products. And I can tell you that all of the embodied carbon figures that we've published in the brochure I mentioned and the embodied carbon figures that I used in the presentation, they include any refrigerant that is supplied in the unit from the factory. And the way that embodied carbon is calculated as well is there is a life cycle of that product. So if we use TM65's embodied carbon calculation methodology, the assumed life cycle is 15 years. And the assumption is that over those 15 years, a little bit of that refrigerant will leak out each year. And as it leaks out, that impacts climate change because refrigerant has a global warming potential equivalent to CO2. Some refrigerants are worse than others. The example I used was a unit that has R32 refrigerant in it, and that's got a global warming potential of just over 600, which means for every 1 kilogram of that refrigerant that leaks into the atmosphere, it's the equivalent of over 600 kilograms of carbon dioxide leaking into the atmosphere. But those calculations fully include all of the refrigerant that is in the system. The only place for Poppy, who sounds quite into this topic, the only thing that to be careful of is if you were looking at any kind of system that's got refrigerant pipework between an outdoor unit and an indoor unit, then the embodied carbon calculations wouldn't include any additional refrigerant that you put in that pipework between the outdoor and the indoor, because as a manufacturer, we wouldn't know how long that pipework was going to be, and therefore we wouldn't know how much refrigerant was going to go in there. But certainly all factory charge is included.
Great. We've got a minute left, and we've got quite a complex question from Jason. Let's see how we can do with this in 40 seconds. Do Mitsubishi produce verified EPDs for their HVAC products rather than TM65 data? I understand that EPD data for HVAC systems is hard to produce.
Yeah, it is. And that's the reason why we haven't got a full suite of EPDs for all of our products. But I can assure him that we're absolutely trying to move in that direction. EPDs are currently quite difficult for complex M&E products. But yeah, the same people that were involved in producing all of the embodied carbon calculations under TM65 are currently working to try and move forward with releasing EPD data as well. But as we sit here today, I haven't got one I can share with you, but I can tell him that we're definitely working very hard on that in the background.
That's good news. He dealt with that in less than 40 seconds, which is very impressive. So thanks, Chris. It was great having your insight today on retrofit and helping to explore the role that heat pumps can play in reaching the carbon targets and the increasing role they're obviously going to play and the increasing knowledge that the sector is going to need of the products.